So chapter 3 is all about functions and their graphs. So in section 3.1, we're just going to talk about functions generally. So we're first going to determine whether a relation is a function. So we'll need to talk about what is a relation, and then how do we decide if it's a function. Then we're going to find the value of a function. Find the difference quotient of a function, and this is a pre-calculus concept. Then we're going to find the domain of a function. Defined by an equation. And the last objective is going to be to form the sum, difference, product, and quotient of two functions. So you can use FN as the abbreviation for function. That'll save you a lot of writing here. So the first objective, we're going to determine whether a relation is a function. So if the value of one quantity can be related to the value of another quantity, we say there is a relationship between them, or a relation for short. So there's lots of things that are like this. For instance, your weight is related to the number of calories that you eat. Your gas mileage is related to the speed you drive. Lots and lots of things are related. So the set of all inputs for a relation is called the domain, and the set of all outputs is called the range. And these things don't necessarily have to be numbers. Inputs and outputs can really be anything. So some examples, I mentioned a couple. See if you can think of some more. The height of the water in a swimming pool is related to the temperature as the water evaporates. So a map is one of the many ways to illustrate a relation. So here is a map of a relation, just things that are related to each other. So for this one, it's the number of representatives in the House of Representatives, and the state of Alaska has 1. So we show the state of Alaska being joined to the number 1. Then Arizona has 9 representatives, California has 53, and so on. So we can use ordered pairs to express this relationship, and it would look like this. You'd say the set of, in parentheses, Alaska, comma, 1. So that's the first item in a list, the first ordered pair in the list. Then the next item in the list is Arizona, comma, 9. So that's an ordered pair that says state, comma, number of representatives. Then for California, we would have 53, comma. Colorado has 7, comma. Florida, 27, comma, North Dakota, 1, and then put the closed set bracket. So this is using ordered pairs to express a relationship. Now, a relation may be a function. The conditions for being a function are more strict than the conditions for being a relation. It's harder to get to be a function. It's a narrower opening that you have to get through. So this is my favorite example for talking about functions, where we have a pricing relation where we say, here's the item and here's its price. And a function requires that every item has a price and every item has only one price. So you can say both of those at the same time by saying each item has exactly one price. So for instance, if coffee is 69 cents, hot dog is 89, soda is 99, chips are 79, that is a function because each item has a price and each item has only one price. If coffee is 69 cents and 79 cents, then this is not a function because coffee has two prices. So think about the cashier. They don't know what to charge for the coffee. And this is fine that soda and chips have the same price because each item, soda has a price of 99 cents, chips has one price of 99 cents. So that's perfectly fine. You could have everything in the store cost 69 cents or 79 cents, and that would be a function. It's that each item has to have only one price. So formally, we have this definition that says, let X and Y be two non-empty sets a function, and this is the official Mathieu language, from X into Y, is a relation that associates with each element of X exactly one element of Y. So if you have a set that's called capital X and a set that's called capital Y, it says that for each thing in set X, it's associated with or maps to exactly one element in Y. So determining whether a relation is a function, we just have to decide if each item in the domain connects to exactly one item in the range. So if each item has only one price, doesn't matter what the price is, then this relation is a function. So this is a pricing function. And then if chips have two prices, this is not a function. So if a function is presented as a set of ordered pairs, then we have to determine whether each x value has one and only one y value. So in these examples, you're given ordered pairs. I like to put them in this arrangement of domain and range. The domain is all the first items in the ordered pair, so 1, 2, 3, 4. The range is the second items, 4, 5, 6, 7. 1 is associated with 4, 2 is associated with 5, 3 with 6, and 4 with 7. So this is a function. So let's do the next two in class and talk about them. So relations can be expressed as maps. So that what we were just looking at with the arrows here, those are maps. Ordered pairs. So see how we went back and forth between ordered pairs and maps. And they can also be expressed as equations when the sets of the x's and the y's are all numbers. So let's see, how do we decide whether an equation is a function? So we're still asking the same question. For every value of x, is there one and only one value of y associated with it? So for each value of x, if we pick x values, and the way we find the y values is to cube the x values. No matter what x is, -1, 0, 1, we're going to get a y value, only one y value that we get by cubing the number. So this is a function. But then I have x is y squared. So let's think about how this one goes. If I have x values, and then x is y squared, I can get more than one. Let's see. If I have y is 2, then x is 4. But if I have y is negative 2, then that also comes from x is 4. So if I had a table and I had y values and x values, 4 would map to 2 and to negative 2. So this is not a function because one x value generates two different y values. Okay, so objective 2 is to find the value of a function. And we would all say plug in to the function. Evaluate is the fancy word. So here's some vocabulary that we need. The x variable is called the independent variable and is always graphed on the horizontal axis. The variable y is called the dependent variable and is always graphed on the vertical axis. So it's just so that we all can make sense of the graphs. So function notation, we read this notation as f of x. So formally what it means is the y value associated with this value of x. So it means evaluate the function f at some particular value. So for this example function, we'll do some of these in class, but let's start by doing some here. F of 0 equals 0 over 0 squared plus 1, which is 0. So f of 0 equals 0. So we know the point 0, 0 is on this graph. So keep reminding yourself the connection between the algebra and the graph. So b, let's find f of 1 equals 1 over 1 squared plus 1. So this would be 1/2. So f of 1 equals 1/2. So the point 1 comma 1/2 is on this graph. Okay, and then let's do f of negative 1. Remembering that you have to put parentheses around the number if it's to a power. So this is going to be negative 1/2. So f of negative 1 is negative 1/2. And we'll do the rest in class together. So objective 3 is find the difference quotient of a function. And this one's really important and kind of complex. So I'm going to go ahead and make a separate movie starting from here.